Welcome to this explainer. I'm putting on my senior AI hiring manager hat today because I want to give you the ultimate cheat code for passing a high-stakes AI system design interview. We're going to cover exactly what separates the junior candidates from the truly senior engineers when it comes to fine-tuning large language models for production. Picture this. You're sitting across from me in an interview, and you say something like, "Hey, let's just full fine-tune the model so it learns our changing prices." Honestly, I instantly know you're not ready for production AI engineering. It's one of the most common things I hear, and man, it is a guaranteed interview ender. So what does this all mean? Why exactly does that answer just completely tank an AI system design interview? Well, we're going to break down exactly why using fine-tuning for dynamic data is a massive red flag. As a senior candidate, you absolutely have to prove you understand behavior adaptation, cost, latency, data quality, and deployment. Okay, let's look at the agenda. These are the 5 critical areas I evaluate every single senior candidate on. First, the core mental model. Second, the PEFT toolbelt. Third, alignment evolution. Fourth, enterprise system design. And finally, common engineering traps. Let's get right into it. Number 1, the core mental model, fine-tuning versus RAG. Because look, before we even talk about how to tune a model, I need to know if you actually know when to tune a model. A junior engineer usually thinks fine-tuning just adds knowledge, but a senior engineer, they know the fundamental difference. Fine-tuning updates behavior, format, and style by training on task examples. RAG, or Retrieval Augmented Generation, adds external knowledge without changing the model weights. Basically, you change parameters for behavior, but you change context for facts. Here is the absolute boundary line. You do fine-tune when you need a consistent response format or a domain-specific tone, and you have tons of high-quality examples. But you do not touch those weights if the model is just missing external knowledge. And definitely don't do it if data like pricing or inventory changes frequently, or if you need guaranteed factuality. Fine-tuning does not guarantee truth, period. All right, moving to section 2, the PEFT toolbelt, adapting with efficiency. Let's open up your technical toolbelt here, because in a real production environment, full fine-tuning every single parameter of a massive model is just way too expensive to train and serve at scale. This brings us to LoRA, or low-rank adaptation. It's the industry standard for a reason. Instead of retraining everything, LoRA freezes the base model weights and trains these small, low-rank matrices injected right into the transformer layers. It dramatically reduces memory. And the real kicker for production, in deployment, you can often just merge these weights directly into the base model to avoid any extra inference latency, a total game changer. Now, if you sit in my interview and tell me you always use QLoRA, I'm going to push back. A senior engineer knows QLoRA, which puts LoRA on a 4-bit quantized base, is strictly better only when extreme GPU memory reduction is your absolute bottleneck. The trade-off? It introduces quantization instability, and it can actually mean slower training. You've got to understand those trade-offs. We also have adapter layers. These are extra trainable modules inserted inside the transformer layers. Now, both LoRA and adapters offer really strong modularity. That's incredible for multi-tenant systems where different clients need different behaviors. But there's a catch with latency. Unlike LoRA, which can be merged, inserting these extra modules can actually hit your latency budgets hard during the forward pass. Section 3, Alignment Evolution from RLHF to ORPO. Once the model actually learns the task via supervised fine-tuning, I need to see how you handle preference optimization. The alignment pipeline has evolved so fast. We started with classical RLHF, supervised fine-tuning, training entirely separate reward models, and doing complex PPO optimization. But that was expensive and, honestly, pretty unstable. So the industry moved down to DPO, directly on preference pairs. And now we're even seeing ORPO, reference model free tuning, just to save on compute overhead. Let's zoom in on DPO, direct preference optimization. This became massively popular because it literally skips that unstable PPO step. It directly optimizes on chosen and rejected response pairs without a separate reward model or online RL loop. It's just so much simpler and significantly more stable to operationalize. But here's the thing, alignment isn't free. If you just blindly apply RLHF, you might trigger massive failure modes. We're talking reward hacking, over-optimization against weak reward models, loss of general capability, verbosity bias,
or safety over refusal, where the model just refuses to answer basic questions. Oh, and the ridiculously high cost of preference data. You really have to know the risks.
All right, Section 4, Enterprise System Design, Building the Architecture. Now we hit the whiteboard. Your task? Build an enterprise customer support assistant that handles multiple clients without hallucinating. Let's see how a senior engineer actually maps this out. A winning candidate doesn't just throw a giant prompt at an LLM. No way. They break it down into modular layers. Step 1, knowledge layer, using RAG for changing policies. Step 2, behavior layer, using SFT or LoRA for tone and formatting. Step 3, preference layer, using DPO or ORPO for conciseness. Step 4, safety and eval layer for validation. And finally, Step 5, deployment layer, routing those specific LoRA adapters over a single base model. As your hiring manager, I also need to see your evaluation strategy. You must strictly separate offline from online evaluation. Offline evaluation is all about model quality, exact match, classification accuracy, hallucination rate, safety violations. But online evaluation, that's operational quality. That's user satisfaction, human escalation rate, live latency, and actual cost per request. You absolutely have to track both. Section 5, Common Engineering Traps, Myth versus Reality. To wrap up this interview gauntlet, let's rapid fire through the massive red flags that get candidates instantly rejected. Trap number 1. Junior engineers almost always say this: more data is always better for fine-tuning. They literally just want to throw the entire raw data lake at the model and cross their fingers. Actually, scratch that. The reality is strictly quality over quantity. Bad fine-tuning data can actually make the model perform worse than the base model. A smaller, incredibly clean dataset with perfect labels will outperform a massive, noisy dataset every single time, for sure. Trap number 2, DPO solves hallucination. This is another huge one, assuming that preference tuning just magically makes the language model more truthful. Reality check. Fine-tuning does not guarantee truth. DPO improves preference alignment, not factual grounding. It makes the model sound more concise or helpful, but it doesn't fix facts. You still absolutely need retrievals, citations, and robust offline evals for factual accuracy. So, as we wrap up this masterclass, next time you look at your AI architecture, ask yourself, are you making practical trade-off-aware design decisions? Are you building a brittle monolith or a modular evaluator-driven AI system? Master your toolbelt, avoid the naive traps, and you'll crush the system design gauntlet. Keep building, and I'll catch you in the next explainer.